Alright, in this video we're going to look at one of the final topics in the chemical kinetics unit. This is called the Arrhenius Equation, which describes the temperature dependence of rate constants. Stop and think about this for a minute and you'll realize quickly why rate constants do have to indeed be temperature dependent. We'll look at a reaction here which is from biology or biochemistry. We have sucrose, C12H22O11, and we're going to do the acid hydrolysis of the sucrose. So it's catalyzed by hydrochloric acid with water, and the sucrose, which is a disaccharide, breaks apart into two simple monosaccharides, or simple sugars, glucose and fructose. In this reaction, we're going to see some data about it in just a minute. Imagine that it were done at situations with different temperatures but identical concentrations of acid and sucrose. So we are using exactly the same concentrations of the reactants, but we're going to simply do the reaction at different temperatures. Well, what would we observe? What would we expect to observe? Collision theory tells us that as we raise the temperature, the reactions are going to get more kinetic energy. As they get more kinetic energy, there'll be a greater frequency of collisions. That by itself should cause an increase in the reaction rate. But they're also going to be, each collision happening with greater amounts of energy. And so with greater energy per collision, more of the collisions will have the required activation energy, and so that will also cause the rate to increase. Bottom line is that the rate of the reaction is increasing even though we're keeping the reactant concentrations constant. If you think of a rate law, which says rate is equal to the differential rate law, rate is equal to the rate constant times the sucrose concentration to some power x, and the acid concentration, HCl, to some power y. We'll ignore the water for this discussion. If it's happening in water, water's concentration will be essentially constant because it's so large. In the rate law, if the rate is increasing because we're raising temperature, but the concentrations are not changing because we held them constant in the experiment, then the only way to explain the faster rate would be if the value of k were to increase. So we can see there that that simple example that the rate constant must increase when temperature is increased as well. So that's a simple way to understand what's happening. The relationship between temperature and rate constants, though, is not simple. It was studied by a Swedish chemist by the name of Arrhenius. He discovered this logarithmic or exponential relationship. The rate constant was equal to something called the Pre-Exponential Factor, that's what we now refer to it as, times e, that's the base of the natural logarithm, raised to the power of negative Ea, the activation energy, divided by RT, where R is the ideal gas constant, and we're going to use the SI value for R, so 8.314, and T is the Kelvin or SI value for temperature. Now, one thing to remember in this equation is that the activation energy is also going to be in SI units, so it's going to be joules per mole, okay, joules per mole, not the more familiar kilojoules per mole. Now, that is technically the exponential form of the Arrhenius equation, and it's not one that we use very often. What we use much more often is a logarithmic form of that equation. If you just convert the exponential form into a logarithmic form, you get this equation. Natural log of rate constant is negative Ea over R, the activation energy and the ideal gas constant, times 1 over the Kelvin temperature plus the natural log of that exponential pre-exponential factor. Now, I didn't mention it earlier, but this pre-exponential factor is related to the frequency of the collisions happening as well as to the orientation of the collisions. Having said that, it's not something that we're typically going to be interested in. So the value of A is not something that we would normally calculate. We're much more interested in the rate constants and the activation energies in this equation. Now, when you examine that equation, as ugly as it might look at first, you notice it has that very familiar form, y is equal to mx plus b. So it has the form of a straight line. If we were to graph on the x-axis the reciprocal of Kelvin temperatures, and on the y-axis the natural log of rate constants, we should get a straight line. Now the slope of that line is negative EA over R. If you think about that for a minute, R is a positive number, the ideal gas constant, 8.314. EA is a positive number, the activation energy in joules per mole. This negative sign out front is going to mean that the slope of our line is negative. So a graph like this should produce, with natural log of rate constant and 1 over t, it should produce a falling straight line. The slope of that falling line is going to give you negative EA over R. So if you know the slope of that line, you'll be able to calculate the value of the activation energy for the reaction. Let's try this with a set of rate constants measured at different temperatures. If you have a graphing calculator, you can enter this data yourself and try to graph it. I'm going to do that for you here on my calculator. So if you want to pause the video and enter these numbers, I'm going to do that here for you as well. So I've got my calculator. I'm going to press the Stat button, and then I'm going to choose option number 1, Edit. Here are some lists, and you'll notice that I've already pre-entered the data. So the temperatures are 24 degrees Celsius ranging down to 40 degrees Celsius. The rate constants, I'm not sure if you can read that in the video, it's 4.8 times 10 to the minus 3 per seconds, and they'll go all the way up to 32 times 10 to the minus 3 per seconds. So I've entered those numbers here in list 1 and list 2. Now in our graph, we know that we don't want to graph rate constants and temperature. We want to graph the natural log of rate constants, and we want to graph the reciprocal of temperature, and that temperature can't be in Celsius. It has to be in the Kelvin temperature scale. So let's do that. I'm going to go to list 3, so I'm going to put the cursor up on the L3 symbol. Notice at the bottom of the calculator screen it says L3 equals. In fact, let me zoom in so you can see that a bit better. Pardon the noise of the camera. There we go. So L3 equals, let's take the reciprocal of Kelvin temperatures. The temperatures are in list 1. So I'm going to open a bracket, the reciprocal of the Kelvin temperatures. So let's take L1, which is in Celsius, and to convert Celsius to Kelvin, we simply add 273.15. And then the reciprocal of those Kelvin temperatures, I'm going to press the x to the minus 1 button. You could also just type 1 divided by that bracket as well. So we're converting L1, the Celsius temperatures, to Kelvin, and then we're taking the reciprocal. So there's list 3, the reciprocal of the Kelvin temperatures. Let's go to list 4, and in list 4 we're going to want to take the natural log of the rate constants. The rate constants are in list 2 on the calculator, so I put my cursor up on the L4 symbol. At the bottom of the screen it says L4 equals, so we'll take the natural logarithm of list 2 and enter. So now list 3 has the reciprocal of Kelvin temperature, list 4 has the natural log of rate constant. We can create a scatter plot. So on the calculator we go to the stat plot option, which is right here under the calculator screen. So second function, stat plot. I'll choose plot number 1 and turn it on if it's not already on. We want the scatter plot, the first option. And my X list is not list 1, it's actually list 3. That's where the reciprocal of Kelvin temperatures were. And my Y list is list 4, where the natural log of rate constants were. To see the graph, we press the zoom button underneath the screen, zoom, and then option number 9, I'll just scroll down so you can see it. Option number 9 says zoom stat. So that's what we want to choose. And sure enough, we get a nice linear graph, a straight line graph. So if you want to sketch that, that's the graph of natural log k versus 1 over t. Now we want the slope of that graph. So let's use the calculator. We'll press the Stat menu again. We'll go to the right to the Calc options, and then option number 4 is linear regression, which tells us the equation of the line through our data. So linear regression, I'm going to tell the calculator list 3 is my x list, comma, list 4 is my y list. If I only want to see the equation of the line, I could just press enter, but I'm also going to be lazy and get the calculator to graph this for me. So I'll put another comma, and I'm going to tell it to graph it as one of my functions. So I press the variables button, vars, and then I go to y variables and functions, and I'll graph it as the first function, y1. So we're telling the calculator, find the equation of the line, do linear regression, using the data that was in list 3 and list 4, the x list first and then the y list, and then we're saying graph that line as function y1 on the graphing calculator. Press enter. There's the slope of our line, negative 11,018, or negative 11,019 if we round it off. And if we press the graph button, we can see the original graph now has a nice straight line going through it. And looking at the data, it certainly appears that this was not real data because it's so perfectly linear. If it were experimental data, we'd expect to see some error in that. So I'm going to zoom back out. And let's just quickly sketch what we just saw. So graphing that data, natural log of rate constant versus 1 over t gave us a straight line graph, and we know that the slope of that graph is equal to negative EA over R, and the slope of our graph was negative 11,019. That's too many significant digits, but we'll just leave it there. Let's now use that to calculate the value of the activation energy. Okay, now the the slope also has units, right? The natural log axis is unitless. The 1 over Kelvin temperature means the units here are reciprocal K. If we want to find EA, it's going to equal our slope multiplied by negative R, right? M times negative R will give me EA. So that's going to equal the slope, negative 11,019, times R, negative 8.314. And notice we're going to get a positive answer for activation energy. It must be a positive quantity. So negative 11,019 times negative 8.314. We get a large number, 91,000, I'll just round it off, 600. Now it's so large because the units, you remember, are joules per mole. If we want to convert that by dividing by 1,000, we get 91.6 kilojoules per mole. Alright, so there's using data like that to graphically determine an activation energy using the calculator. Now often we don't have a whole set of data like that, or more likely many of us don't own a graphing calculator to easily graph with, so we want to algebraically be able to determine activation energies. To do that, this is not quite as accurate because it's going to involve only 2 data points. So this is a version of the Arrhenius equation, which I'm not going to derive for you, but it is easily derived from the earlier equation. We take the natural log of 2 rate constants, K2 over K1, and that's going to equal negative EA over R times the reciprocal of the second temperature minus the reciprocal of the first temperature. So you just have to match this temperature T2 with this rate constant K2, this temperature T1 with this rate constant T1. Remember that R is 8.314, and remember that the activation energy must be in joules per mole. Okay, if they're given it in a question, it must be joules per mole, not kilojoules per mole. So let's use the equation, and we're going to take the first and last data points from that earlier data table to calculate EA for the reaction algebraically. So 24 degrees, 4.8 times 10 to the minus 3, and 40 degrees, 32 times 10 to the minus 3. So using those two data points, let's calculate EA. So we have K1. It doesn't really matter which point you call 1 or 2, but just be consistent. So K1 was 4.8 times 10 to the minus 3 per seconds. T1 was 24 degrees Celsius. K2 is 32 times 10 to the minus 3 per seconds. And T2 was 40 degrees Celsius. So using that data, let's calculate algebraically the value of EA. So I'm going to take the equation above and substitute this information in. So we get the natural logarithm of K2 over K1, so 32 times 10 to the minus 3 over 4.8 times 10 to the minus 3, and that's going to equal negative EA over R, 8.314, times, now when I put the reciprocals in, I usually just type in a number to the power of minus 1. But remember that the temperatures can't be in Celsius, they have to be in Kelvin. So for T2, that'll be 40 degrees Celsius, we add 273 to that, and we'll get 313 Kelvin reciprocal, minus T1 reciprocal. T1 was 24 degrees, so that's going to be 297 Kelvin reciprocal. Now we can evaluate the stuff on the left just with our calculator, so let's take the natural logarithm of 32 times 10 to the minus 3 divided by 4.8 times 10 to the minus 3 equals 1.90. Negative EA over R, and we can evaluate what's in the brackets there as well. So 313 reciprocal minus 297 reciprocal equals negative 1.72 times 10 to the minus 4. So now just do some simple algebra. 1.9 times negative 8.314, and then divide by this bracket, and we'll have EA. So EA will equal, one more time, that's going to be 1.9 times negative 8.314, and divide by negative 1.72 times 10 to the minus 4. Be sure you're using the scientific notation button on the calculator. You're not typing in negative 1.72 and then the time symbol. You're using the EE button to do scientific notation. The EE button on the graphing calculator is right here above the comma symbol. So press enter, and we get 91,800 joules per mole, which will be 91.8 kilojoules per mole. And notice when we compare that, it's very similar to what we got graphically, 91.6. The reason they're so similar is because the data was so perfect. The line was perfectly straight. If this were more realistic with experimental data with error in it, you would find that the graphical value for EA is probably significantly different. Maybe instead of 91.8, you might have had 92.4 or 90.3, something close to what you got from the graphical approach, but this two-point approach would have had some more error in it. It's always better to use more data when possible. So now let's do another calculation. Let's calculate the value of the rate constant at 10 degrees Celsius. And to do that, we're going to use the EA that we just found. So now we need one other point. We can use one of these points here if we want, or we can use a different point from the table. I'm going to use this point here as one of my 2 points. So I'm going to say K1 is 4.8 times 10 to the minus 3 per seconds. T1 is 24 degrees Celsius. Let's zoom in a bit so you can see that. We want K2, which we don't know, so I'll just put a question mark there. And we want T2, which is 10 degrees Celsius. And now notice we know EA 91.8 kilojoules per mole. So let's plug this into the Arrhenius equation for 2 points. So we'll say natural log of K2 over 4.8 times 10 to the minus 3 is equal to negative, now be careful here, when you're using this equation, remember that the activation energy must be in joules per mole. So 91.8 becomes 91,800 joules per mole, divided by R, and then remember that the temperatures must be in Kelvin, so the first T2 is 10 degrees, that's going to be 283 Kelvin reciprocal, minus T1, which was 297 Kelvin reciprocal. Now notice everything on the right can just be evaluated. It's just numbers, so let's grab a calculator and do that. So we have negative 91,800 divided by R times bracket 283 reciprocal minus 297 reciprocal equals negative 1.84. So we get the natural logarithm of K2 over 4.8 times 10 to the minus 3 is equal to negative 1.84. Now please be careful here. Some people want at this point to multiply both sides by 4.8 times 10 to the minus 3. You can't do that because the K1 in this case is trapped, it's held within the natural logarithm. So what we need to do is undo the natural logarithm before we go any further. Remember that the base of the natural logarithm is the number e, so it really means log base e of this is negative 1.84. And what we're going to do is just switch the logarithmic form back to exponential form by saying e to the power of negative 1.84 must equal what's in this bracket here. So K2 over 4.8 times 10 to the minus 3. If you're not that familiar using logarithms, that's probably confusing to you, but that's how logarithms work. We have a logarithmic form of the equation, and this is the equivalent exponential form of the equation. So now the thing on the left there, e to the negative 1.84, we can grab a calculator and evaluate that. Right above the natural logarithm button on the calculator, it says e to the power of x. So on my calculator, I go second function ln, e to the power of negative 1.84 is equal to 0.159. So that's 0.159 equals this stuff here. So to find K2, I'm just going to multiply 0.159 by 4.8 times 10 to the minus 3. So K2 will equal 0.159 times 4.8 times 10 to the minus 3. So 7.6 times 10 to the minus 4. The units for K will be the same as they were in the data table, which were per seconds. Now, is the answer reasonable? Since this is slightly lower temperature, we expect it to be a slightly lower value of K, and sure enough, it is. 7.6 times 10 to the minus 4 is just a little bit less than the 10 to the minus 3s that we were getting at the higher temperatures. So there you have it. We've calculated a rate constant at a given temperature using the 2-point formula, and we calculated the activation energy using the 2-point formula. The third thing you might be asked to calculate, of course, would be to find a temperature. If you were given 2 rate constants, the activation energy, and 1 temperature, you could find a missing temperature as well. There's another relatively common type of problem with the Arrhenius equation. So just to recap, if you have a data table like this and you're with several rate constants at several different temperatures, then you want to use this form of the Arrhenius equation and your graphing calculator to graphically determine the activation energy. If, on the other hand, you're given only 2 points and asked for an activation energy, then you want to use this 2-point version of the formula, and you could also use that formula to calculate things like a rate constant or a temperature.